Hello, everybody. I'm Dr. Shafiq, and I would like to welcome all of you in this video session. Today, we'll be talking about triaxial test to find out the shear strength of soil. Okay? So triaxial tests are done to overcome the two greatest shortcomings of the direct shear test. So you can remember the disadvantages of direct shear test, and you can see that basically they cannot apply confining stress and they cannot control the drainage. So to overcome these two shortcomings, actually we do the triaxial test. First of all, they can apply appropriate confining stress. Okay, so if you think about the field, so if the soil is, let's say, 50 feet or 30 feet below the surface, then basically the soil has a confining stress there. Okay, so in this test, triaxial test, actually we can apply that confining stress. Okay, and the second thing is we can control the drainage um, based on the field situation. So thus the state of stress is known for triaxial test, and it's much easier to draw the Mohr circle from there, and you can find out the other parameters like the the soil strength parameters like phi and C easily from this triaxial test. Now let's see here. This is your specimens sitting on a porous, stone, and you can see you can just apply sigma 3, which is called the all-around pressure or cell pressure. And then once the soil is allowed to, um, have that consolidation pressure, then basically then we apply this shear. So this test has basically two stages. The first stage, we apply the confining pressure. And the second stage is we apply that vertical force or stress to shear that specimen. Okay, so you can see this is sigma 3, and if this one is called the deviator stress, which is equal to P by A. P is the force here, area is this area of that surface here. So your sigma 1 would be sigma 3 plus the deviator stress. Okay, since you see that we are not applying any shear here or here, so your tau xy equal to 0. So this is your principal plane. Okay, sigma 1 is called the major principal stress, and sigma 3 is called the minor principal stress. And this is your deviator stress, which is basically the difference between sigma 1 and sigma 3. Okay, now this is a triaxial test instrument. You can see here, this is, you control the cell pressure and you can apply the pressure from there. This is the diagram of that, triaxial cell here. This one is here. You can see this is a porous stone. This is basically your specimen here. There is another porous stone here. And then you can see you can apply force from, cell pressure from here. Okay. So you can change that cell pressure or confining pressure using this instrument here. Okay. And you can see that how, the volume of that thing is changing from there. Okay. Once you get that consolidation, if you allow it consolidated, then basically you start applying this load here. Okay. For shearing. Now we have three different triaxial tests based on the drainage condition during the two stages. What is that two stages? One is during applying the confining pressure and during applying the shear. Okay. So first of all, we have CD test, which is called consolidated direct shear test, consolidated drain shear test, in which the drainage is allowed both stages. Okay. You have UU test, means like unconsolidated undrained test. So drainage is not allowed in any of the stages. Okay. In the middle, you have CU test or consolidated undrained test, means like drainage is allowed the first stage of the test. You allowed to consolidate the soil when you apply the confining pressure. But when you apply the shear, then basically you don't allow the soil to drain at that situation. So basically, um, this one will produce the drain shear strength, this one will produce the undrained shear strength, and this one will produce the shear strength in between these two uh, shear strength. Okay. Now, based on the field situation, we have to pick like which one is which test you are gonna do, or what strength of soil you are gonna use for your calculation, for your design and everything. Okay, so um, I'll talk about that, like how you can choose each of the situation. Now let's start with our consolidation drain test. Oh no, before that we have the advantages of triaxial test here. As I said earlier, that the state of a stress state is known. You can apply confining stress. Drainage can be controlled. We already talked about that, and this is a very reliable test. Okay, but what is the disadvantage of that one? It's require expertise to do that test, expensive and time consuming. Um, Whether like it's maybe like for direct shear test, it might cost like 250 to 350, but for triaxial test, they could charge you from $1,000 to $1,500. Okay, the range is a little high, depends on like which triaxial test you are going to do, because U test is very fast. On the other hand, CD test is very, very slow. So it depends on which one you are picking for your um, triaxial test. Okay. Now this is called the consolidated drain test. We are going to discuss that one first. So from the name, you can understand that first part is the stage one, and this is stage two. Stage one, actually, when we apply the confining pressure, and stage two is when we apply the shear. Okay, so both cases we see that you are going to allow consolidation, means like the drainage is open, and when you apply the shear, then you are allowing the, because it's saying it's drained, so it means like the drainage valve is open. Okay, so CD tests are done on clay soil when the construction over that soil is slow enough that the excess pore water pressure due to the loading from the new structure can be dissipated during the construction, or faster than the construction. So it's not only about the soil, it's also the situation you are talking about. How fast is your construction? How thick is the layer you are talking about? If you see that the soil can drain, or the consolidation can occur, or the occur uh, before the construction period, and you can see the pace of construction is slow enough that um, the excess pore water pressure that develops because of the new structure can dissipate very quickly with the construction. That's basically the situation we are talking about. So basically, your consolidation drain test will provide you the drain test, which is actually the highest, like a strength for um, any soil, clay soil. Okay. Uh, Now you can see the drainage allowed during the applying both confining stress and deviator stress. We already talked about that. But if you say the state of stress at both stages of the CD test, so you can see this is the first stage. You can see I'm applying sigma 3 or confining stress here, and I'm applying in such a way that your pore water pressure would be 0, means like I'm allowing them to consolidate it, okay? So once this one is consolidated, then I'm actually applying the deviator stress from the top, okay? And I'm applying the deviator stress so slowly that the excess pore water pressure will be 0 in most of the time, okay? So that's basically the two stages. So during confining stress application, and this is during deviator stress application, both cases, drain is allowed so that your pore water pressure is actually 0. One thing I must, say that one here, that actually, even though we are saying that this is the force for shearing, but you can see actually we don't apply any shear force here. We actually use the normal force in this particular plane, but that would cause the stress transformation at different, plane of the soil, and the soil will particularly fail at an angle here, which we have discussed in our first video, and I'll talk about that again in this video too. Okay, now let's see that how we do the CD test. Okay, so first of all, trim undisturbed test specimen or compacted sample place so that the specified field density and the water content remain same. If you can get the field, soil, that would be the best thing, um, to run that test. Now enclose this one with a membrane, plastic membrane, and then put that one in the triaxial cell. Raise cell pressure and back pressure with the drainage valve open until a specimen is fully saturated. Okay, that's the part of saturation. Why we need the saturation? Because soil shows minimum, especially clay soil, shows minimum strength when the soil is completely saturated. Okay, so when we construct anything because of rain or something flood, the soil is to be, you know, uh, completely saturated sometime, and that time this one will show the lowest strength. So we have to make sure that the structure doesn't fail when the soil doesn't, um, when the soil is completely saturated. Okay. So when we talk about shear strength, actually shear strength, it's kind of implied there that when the shear strength, when the soil is completely saturated. Okay. We don't say that one, like hey, what is the shear strength of the soil when the soil is completely saturated? Because you don't need to. It's kind of implied. Okay. Now, to make sure that whether your soil is completely saturated, we check that B value. We'll talk about that. That big B value is nothing but the change in pore water pressure divided by the change in your cell pressure. So if you change your cell pressure, let's say 10 psi, then basically your pore water pressure has to be changed also 10 psi. Okay, in that situation, we can say that the soil is completely saturated. If soil is not completely saturated, there are some air bubbles there, then your B value means like your pore water pressure would be less than your cell pressure that what you apply. Means like the soil is not saturated yet. Once the saturation is complete, then basically you keep the drainage valve open and apply the um, apply the the appropriate sigma 3, means like you're confining stress. Okay, and keep that valve open during that time so that any excess pore water pressure will be dissipated, and actually the soil will be 100% consolidated. Once your pore water pressure is zero, which means like your 100% consolidation has occurred, then basically you can start increasing your deviator stress using an axial load to failure very slowly so that again the excess pore water pressure is also zero. Okay, so that's basically your test. Now, these parameters here, as we said earlier, that B equal to UC divided by del sigma 3 or sigma 3, we call that one Skempton's pore water pressure B. Okay, so B is the Skempton's pore water pressure parameter, and then UC is the change in pore water pressure, and sigma 3 is confining pressure. Now, for theoretical values for B at complete saturation, in most of the cases you can see very close to 1. Okay, so it's for normally consolidated soft clay, lightly consolidated soft clay and sealed, over consolidated stiff clay and sand, and very dense sand and very stiff clay at high confining pressure. At that time, you can have very low, which is kind of 0.9, like value for B. Okay, so it's sometimes very difficult to achieve the saturation and make sure all the air inside the soil has been taken off from the soil domain. Okay. Now CD test results. You can see this is axial strain versus your deviator stress. As you are increasing your axial strain, this one is increasing, okay? But the same thing here, but this one is for loose sand or normally consolidated clay. This one is for dense sand and over consolidated clay. For dense sand and over consolidated clay, we see a distinct peak here. Okay. On the other hand, for loose and normally consolidated clay, actually we don't see any peak. Okay. Now you can see this one shows how the volume of the specimen changes with the axial strain. So you can see for loose and normally consolidated clay, actually the volume decreases because they still have a lot of voids there, and soil particle can go there when they are trying to shear each other. But for dense sand and over consolidated clay, because they are highly densely packed, so when they try to shear, that I showed you previously, that they have to come out from there to slide, okay? So they can't slide like this. So they have to come out first and then they can slide. So that would increase the volume slightly, okay? So that's why you can see at the beginning, it's kind of compression and then actually increasing. And then when this one is just coming from here to here and then trying to slide, that time actually the volume remains constant, okay? Now Mohr circle for the CD test. First of all, that CD test for sand and normally consolidated clay. You can see when this one is saying sand or normally consolidated clay, your C is basically 0, okay? So we know that sand doesn't have any cohesion, but clay doesn't have any cohesion when the clay is very, very loose, okay? The loosest condition is actually normally consolidated clay when it got deposited from the soil, like suspension, like that's just dropping at the bottom because of the Brownian motion at the bottom of the lake or something like that. And you take the soil, water off there, you get the sediment, okay? This is very loose soil. So that's called the normally consolidated clay, which doesn't have any cohesion here. So first of all, how we draw the Mohr circle. So we know our sigma 1, we know our sigma 3 and sigma 1 from there. So we can find out the like the center, which is sigma 1 plus sigma 3 divided by 2. And it doesn't have any tau xy. So basically your radius would be sigma 1 minus sigma 3 divided by 2. So you just go there and draw that circle here. Okay. And then you just draw that line here. More Coulomb, like failure envelope. So you just draw that line so that it touches like in any one of that circle. This is for one test. This is for the another test. Okay. You don't need two tests like for sand or normally consolidated soil because you already know one point that this one is going to pass through the origin. Okay. So this one has to be drawn in such a way that this one is kind of like a tangent of that circle here. Okay. Now you already know that you can find out this angle here. We already talked about that theta, or this angle theta, that how this one is gonna, fail and along which plane. That's actually phi is equal to 45 plus phi by 2. Okay. Now you can see here, actually, we are just writing everything like this phi prime because this is effective stress failure surface. At the same time, this is total stress failure envelope. Why is that? Because I did that test so slowly during the consolidation as well as when I apply that axial load that all the time the Porewater pressure was 0. This means your total stress is equal to your effective stress. So basically, this is the same line for your total stress and effective stress, and your Porewater pressure is 0. Okay. Now, what happens like if I do the same test on dense sand or over consolidated clay? Actually, they like over consolidated clay, not like dense sand. So over consolidated clay, you can see that this is your pre-consolidation pressure. Okay, pre-consolidation pressure. So you can see from there, actually, you see up to the pressure for pre-consolidation pressure. This one has a C prime here. On the other hand, as soon as your your consolidation pressure is higher than pre-consolidation pressure, then basically you will see that this one will continue as like this. Okay, so the actual line for over consolidation clay would be something like this. Then as soon as we appear in the pre-consolidation pressure, then basically this one follow that line here, not like this. Okay, so that's basically, you can see this is phi1 prime and this is phi prime. So before the pre-consolidation pressure, this one is phi1 prime and you have C prime. As soon as you go, your stress goes after pre-consolidation pressure, then basically you don't have any, like C for that soil. Okay, so you have basically like two different situations here. One is before pre-consolidation pressure and after pre-consolidation pressure. Okay. Now let's see an example. This one is saying that a consolidated drain triaxial test was conducted on a normally consolidated clay. As soon as they say the normally consolidated clay, this is implied that your C is equal to 0. Okay. If they sand like sand or normally consolidated clay, then basically your C equal to 0. If they say it's over consolidated clay, then basically you have C. Okay, so the test results are given here. Sigma 3 or cell pressure is 276 kilonewton per meter square, and your deviator stress is 276 kilonewton per meter square, same value here. you have to determine the angle of friction. That's basically a shear strength parameter of the soil. The other parameter C is basically 0 for normally consolidated clay. And they're also asking you to find out the angle theta the failure plane makes with the major principal plane, and find out the normal stress sigma and the shear strength tau on the failure plane. Okay. Number D, determine the effective normal stress on the plane of maximum shear stress. Okay. So if we start doing that one, then basically when they are saying normally consolidated clay, this means your C equal to 0. So tau F equal to sigma prime tan phi prime and C equal to 0. So you don't have to put that one here. And your sigma 1 is basically sigma 3 plus deviator stress, which is basically 276 plus 276 equal to 552. So I know my sigma 1, I know my sigma 3. Once I know that one, my phi is basically sine phi is basically sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3. You can also use the other equation like your sigma 1 is equal to sigma 3 tan square 45 plus phi by 2, and you can solve for phi. You will get the same answer. Okay. So your phi prime is sine inverse 0.333. So your angle is phi prime is basically 19.45 degree. Okay. Now they're asking to find out the failure plane with the x-axis. Okay, theta. So theta is basically 45 plus phi by 2. So if you already know the phi prime, so you just plug that phi prime here, and this one is 54.73 degrees. Okay. Now you are trying to find out the shear stress and normal stress in that particular plane that makes like theta equal to 54.73. So we can use that equation here, that your sigma n is equal to sigma 1 plus sigma 3 by 2, sigma 1 minus sigma 3 by 2 cosine twice theta. Your theta is equal to 54.73. So if you plug those values here, you get like 368.03 kilonewton per meter square. Okay. Again, for tau, you see like sigma 1 minus sigma 3 by 2 sine twice theta. Your theta is equal to 54.73. And you already know sigma 1 and sigma 3. If you plug that one, then basically you can see your tau F equal to 130.12 kilonewton per meter square. Okay. Now they're also asking you like the normal stress when your shear is maximum. So when your shear is maximum means like where um, in the Mohr circle, you can just take a look where the shear is maximum. That's actually at the top of that circle, right at the top of the circle, which makes actually 90 degree. So if it makes 90 degree with the x-axis in the Mohr circle, then basically this one has to be 45 degree actual, like angle. So if you find out, if you assume that phi equal to theta is equal to 45 degree and plug that value here, then basically you can get the normal stress at 45 degree plane. Okay. So you can see we are using 90 here. So that's your, so if I want to show that one in our, let's say, Mohr circle, then basically we are talking about this point here. Okay, so this is my Mohr circle. Where is the shear strength is maximum? That has to be here, right? Here. So this is basically 45 degree, like 90 degree. If you just draw a line here, so this one has to be 90 degree in the Mohr circle. So actually the angle is 45. So if you plug that 45 angle there, then basically you'll get that answer here. Okay. Now this is the summary of the CD test. CD test provides the drain shear strength. Since the pore water pressure is zero throughout the test, the effective stress is always equal to the total stress. So your phi is equal to your phi prime. And again, if it is over consolidated soil, then actually your C is equal to your C prime. Okay. The confining stress and deviator stress are applied very slowly to allow the water drain out from the soil. Thus, the test requires significant amount of time. Okay, in some cases, I know that you might have to wait like a couple of weeks to do that test, like 1 week for consolidation and 1 week for shearing. Okay, very slow process. So we also call that one slow test by S test. Okay. Now, consolidated undrained test. So first part you can see is consolidated, means like you are allowing the soil to be consolidated. So you are allowing actually the water to drain out from there, the first part. And the second stage, this is undrained. So no drainage, okay? So if you see that schematics here, or a state of stress at both stage of the CU test, that would be CU actually, CU test, then you can see at the beginning when you are applying during the consolidation, basically drain is allowed and you will see your excess pore water pressure is equal to 0. Okay. But when you are shearing the specimen, that time actually your drain is closed, and that's why you will see a pore water pressure there. How much, we don't know. We have to measure that one from the transducer, but we'll see that there will be some pore water pressure there. Okay, so that's basically the state of stress during 2 stages of that CU test. Now, when we do the CU test in practical situation, CU tests are done on clay soil when the construction over the soil is slow enough so that some part of the excess pore water pressure due to loading from the new structure can be dissipated during the construction. Okay. So the first one, CD test, all the pore water pressure will be gone, means like 100% consolidation occurred. For CU test, actually the significant amount of consolidation occurred during the consolidation, first phase. And then the CU test also done for rapid construction of an environment on a natural slope, rapid drawdown behind an earth dam. We'll talk about that, like what is in future. Just try to remember that one, that rapid drawdown case we use CU values. And then drainage allowed during applying confining stress, but no drainage allowed during applying deviator stress. Now you can just think like, let's say we are making embankment. So in the first year we made like, let's say 5 feet, and then allowed that one to consolidate it for a year. And we came there in the next year and started building on top of that another 5 or 10 feet. This is the kind of like situation when we use CU test here. CU test is usually lower than your drain test, okay? Now, this is the CU test procedure. So first, stream the undisturbed test specimen or compact sample of clay, like to the field density and water content. Then enclose in member and then put that one in triaxial cell. Raise cell pressure and back pressure with drainage valve open until specimen is fully saturated, as determined that the 100% saturation occurred. And again, you see that one your Scampton's B parameter has to be close to 1, okay, to make sure that the soil is saturated. Then close the drainage valve, okay, and then increase the deviator stress. So when you are increasing the deviator stress, that time actually your drainage is closed. So measure the pore water pressure at failure. Okay, so here now we have to measure the pore water pressure at failure as well as we measure the deviator stress at failure. Now we already know, we have talked about that B value, which is very close to 9.99 or close to 1. That's basically the ratio of cell pressure, the pore water pressure. Okay, cell pressure and pore water pressure. Scampton's has basically another pore water pressure, A prime, which is the basically the ratio of deviator stress and pore water pressure. Okay, so this one is applicable in the second stage when you apply the deviator stress. B parameter is actually applied when you apply the confining stress. Okay, so B is for confining stress, A is for deviator stress. So two different stages. Now you can see your A prime value is A bar value is not equal to 1. Okay, it could be for normally consolidated clay, this could be 0.5 to 1. Over consolidated clay actually -5 to 0. Because why this negative value? You can ask that question. Because for over consolidated clay, when you shear the soil, then basically the volume increase. So that will create some suction there rather than like positive pore water pressure. So that's why you will see negative pore water pressure for over consolidated clay. Okay, so that's the main difference between Scampton's pore water pressure A bar and B bar. B bar is always close to 1, which is the ratio between the pore water pressure change because of the confining stress change. On the other hand, A bar is basically the ratio between the pore water pressure changes due to the deviator stress changes. Okay, so this value could be different. Now, you also understand that like when during consolidation, the volume will always decrease. There is no chance that this one will increase, okay? On the other hand, during shearing, for loose sand and normally consolidated clay, the volume decreases. On the other hand, for dense sand and over consolidated clay, actually the volume increases a little bit. When this one try to increase, then basically there will be a suction there. Okay, that's why you have a negative value here. Okay, now they are trying to show you some of the, like the pore water pressure, Scampton's pore water pressure parameter A bar for some, like clay, over consolidated clay. And you can see this is like OCR, over consolidation ratio. So you can see as the over consolidation ratio increases, basically your AF goes towards negative. Okay, goes towards from here, you can see it's going negative. For normally, this one is, let's say normally, this one is normally consolidated soil, right? 1 OCR. So at that time, this is positive. Okay, when you, let's say 2, then you can see this is getting smaller, smaller. If it is 1.5, then basically you would see a little positive here. But as soon as you go more than 2 or 3, then basically you will see this one is going negative. Okay. So volume change during the CU test. So the volume decreased during the consolidation for both normally consolidated and over consolidated clay. Doesn't matter, sand or clay, everything. When you try to consolidate it, then basically the volume decreases. Okay. So excess pore water pressure become nearly zero at the end of the consolidation because the water is allowed to escape. Okay, that's talking about the consolidation phase. So during that time, your pore water pressure is zero here. We just applied sigma 3, which is called the cell pressure or confining pressure. And you can see actually your specimen is, volume is decreasing. Okay, del V is decreasing. Now the second stage, actually when you shear, then basically this one can happen 2 different ways depending on what kind of soil is that. For loose sand and normally consolidated clay and dense sand and over consolidated sand, this one is showing the like that distinct peak, and they don't have any distinct peak here. But when you talk about the volume, then basically for loose sand and normally consolidated clay, the volume goes down. And for dense sand and over consolidated clay, this goes little down first and then increase the volume. Okay. So the same thing, like when you shear any soil, whether this is direct shear test or triaxial test, actually for dense sand and over consolidated soil, the volume try to expand a little bit. And I show you the reason that why this one, like expand a little bit. Like these are the way like the soil are interlocked with each other. So if you try to shear that one, then this one has to come out from there first and then they can move. Okay, so that's why the height of the specimen will be a little higher when you try to shear. Okay, so pore water pressure during shearing of the CU test. Okay, the during shearing deviator stress application in CU test, the excess pore water pressure increase for loose sand and normally consolidated clay as the volume decrease. And then excess pore water pressure decrease for dense sand and consolidated clay as the volume increase. So increased volume means like you have a suction situation there, and your pore water could be negative. Okay. Now you can see actually this is the, for loose sand and normally consolidated clay, this one looks like this. Actually, this is also for dense sand too, because your C equal to 0 in that case, right? So this is your Mohr circle in terms of total stress. If you take the pore water pressure that you measured at the end of the test, then basically you can see for this one, sigma 1, this is sigma 1 minus pore water pressure. That's actually your effective stress. So effective stress plus pore water pressure, that's basically your total stress, right? So this is your total stress. If you subtract the pore water pressure, that's your effective stress. So if you draw that line, this is in terms of total stress. And if you draw that dotted line, this is basically in terms of your effective stress. Now, if you draw that line, that solid line here, then basically that's your phi in terms of total stress. And if you draw that dotted line with this dotted Mohr circle here, then basically you get your phi in terms of your effective stress. Okay, that's basically in terms of your effective stress. So you can see your effective stress, and this is actually your drain case. Okay, when you allow the soil to drain, your pore water pressure would be 0, and basically you will see it from the CD test, you will get this one here, okay? And from your CU test, you can get this one from here. So basically you see that this one is a little bit below that line here, and this one is always smaller than this one here, okay? So that's basically the maximum limit of strength when the soil is completely drained, okay? Means like the pore water pressure can be dissipated during the construction period, okay? If you say, no, it didn't dissipate fully, 50% dissipated or 60% dissipated, then basically you can use this line or this value of phi to, like, but basically all the time this is your engineering judgment that how this one is happening, okay? Now let's see what happens for Mohr cycle CU test over consolidated clay, okay? So over consolidated clay, you can see here, this is like your sigma 3 means your pre-consolidation pressure. So before the pre-consolidation pressure, this one will show you the normal stress is pre-consolidation pressure here. So you show this one is like this line, and after that, this one follow this line here, okay? So here, this equation of that line is sigma tan phi 1 prime. This is the angle plus C, but this one is actually sigma tan phi, because when your normal stress is higher than your pre-consolidation pressure, then basically this is not over-consolidated situation anymore, right? When the pressure, the coming pressure or current pressure is higher than pre-consolidation pressure, then basically it's not over-consolidated situation anymore. So in that situation, this one behaves like a normally consolidated soil, okay? Now this is a CU test results from, uh, normally consolidated clay. Okay, so different type of clay. You can see they are showing the liquid limit, plastic liquidity index, and these are the drain friction angle, okay, that you get from CD test. Or you can get that one from CU test by subtracting the pore water pressure from the total stress, and you can get this one from there, okay? Now here is the example. This one is saying that sample of saturated sand was consolidated under an all-around pressure of 12 pounds per square inch. The axial stress was then increased and drainage was prevented. The specimen failed when the axial deviator stress reached 9.1 psi. The pore water pressure at failure was 6.8 pound per inch square. So determine consolidated undrained angle of shear resistance, means like phi, and also drain friction angle phi prime. So you can see that your sigma 3 is given 12. So your sigma 1 is sigma 3 plus deviator stress, which is given 9.1 here. So your sigma 1 is 21.1, okay? And then your pore water pressure is also given here. But we are not going to use that one here first. We just want to find here like your phi is sine inverse sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3. The difference is here, everything is in terms of total stress. Okay, everything is in terms of total stress. You can write the same equation for effective stress, that phi prime is equal to sine inverse sigma 1 prime minus sigma 3 prime divided by sigma 1 prime plus sigma 3 prime. Okay, So if you go for total stress case, then you can see like your phi is sine inverse sigma 1 minus sigma 3 divided by sigma 1 minus plus sigma 3. So you get 16 degree here. Now, you can easily find out your sigma 1 prime and sigma 3 prime. So what would be your sigma 1 prime? That would be 21.1 minus 6.8. Okay. What would be your sigma 3 prime? That would be 12 minus pore water pressure 6.8. So you can again write that one here. They tried to do that one at the same time, like that, rather than finding out the sigma 1 prime and sigma 3 prime. But you can do it separately and then plug that one in that formula, and you can find out your drained, like phi prime, or like your effective phi prime is actually 27.8. So if I show that one here in this figure, you can see that one is 27.8 and this one is 16. And again, this is basically your 21 sigma 1 minus 6.8. That's actually 14.3. So the difference from here to here is actually your pore water pressure at failure. Okay. Similarly, the distance from here to here, that's actually 6.8. Okay. So 6.8 plus 5.2, that's basically 12. Okay. So you basically draw that one first. If you want to do that one, like not mathematically, but like from graphical method, then you just get your point A, which is sigma 1 plus sigma 3 divided by 2, and then your radius is sigma 1 minus sigma 3 divided by 2. Draw that circle here, and then you subtract the pore water pressure from here. You get here, you subtract the pore water pressure from sigma 3. That's basically your sigma prime 3, and you get this dotted, like Mohr circle for effective stress case. And then you draw that line here, you can find out this angle here. Okay. Now there is another example here that a consolidated undrained triaxial test was conducted on a dense sand with a chamber confining pressure of 14 pounds per feet square. Results showed that phi prime is 27 and phi is 33 degree. Determine the deviator stress and the pore water pressure at failure. Actually, this one has to be the other way around. This one has to be phi 27 and phi prime 33. Anyway, so try to do that one here, that your sigma 1 is equal to sigma 310 square 45 plus phi by 2. So you can find out phi 1 from there. Okay. If you want to do that one like they're using the other equation, that your phi is sine inverse sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3, then basically you can also find out your sigma 1 from there. Okay. So from there, actually, you get your deviator stress, which is nothing but the difference between sigma 1 minus sigma 3. So sigma 1 minus sigma 3, that's your deviator stress. Okay. No, I made a mistake here. Actually, this one is fine because this one happened because the soil is that dense sand, means like actually this one will, the volume will try to increase, and that will create a negative pore water pressure. Okay. So that's what happened here. When you find out the pore water pressure, this one is negative pore water pressure. So when this one is negative pore water pressure, then basically in that case, this dotted line will go to the other side of this one. This one will go like here. So in that situation, your phi prime has to be smaller than your phi. Okay, so that's actually what happened here. Phi prime is smaller than your phi. Okay, so that's the reason that why your pore water pressure was negative, because this is dense sand. Okay, very good. Let's move forward. The summary of the CU test. The CU test provides both drained and undrained shear strength. So from one test, actually, you can get both drained and undrained shear, but this is not completely undrained. So we can, I shouldn't recommend you to use that one as undrained shear strength from your CU test. Okay. Since the valve is closed during shearing, excess pore water pressure develops during shearing. It could be positive or negative, depends on what kind of soil you were talking about. For normally consolidated clay and loose sand, the pore water pressure would be positive, and it would be negative for dense sand and over consolidated soil. The excess pore water pressure can be measured at failure to estimate the effective stress at failure. Phi is always smaller than phi prime is the normal case, but for dense sand and over consolidated clay, this one can be changed. Okay. The consolidation pressure is applied very slowly to allow the water drain out from the soil. However, the applying shear is relatively faster than CD test because it doesn't require to have the pore water pressure 0. So that's why this test usually take less time for compared to CD test. Okay, let's say for CD test, you need 3 days for consolidation and 3 days for shearing. Here, the same soil, if you do that one for CU test, then it will take 3 days for consolidation, but it will take like maybe like 3 hours or 2 hours for your the shear apply when you apply shear, because you can go fast enough, because you don't have to make sure that the pore water pressure is 0. No. So since the valve is closed, you can go much faster rate, and you can just measure the pore water pressure at failure. Okay. This is the UU test, unconsolidated undrained test. So in both cases, both stages of the triaxial test, actually the valve will be closed, and you can go much faster pace here, because you don't have to make sure that your excess pore water pressure is 0. That's why it's also called the rapid test. Okay, so when do you do that one? So UU tests are done on clay soil when the construction over the soil is rapid enough so that the excess pore water pressure due to loading from the new structure cannot be dissipated significantly during the construction. Okay, so it's the practical case. You understand that there is no completely undrained situation occurs in the nature. But for, let's say, over-consolidated high plasticity soil, their hydraulic conductivity is very, very low. So it takes much longer time for consolidation. It can depend on not only the soil, it's also the thickness of the clay layer, right? So if it takes like 20 years, 30 years for consolidation, and you have to just finish your construction like in 2 years, then basically you can assume that, hey, none of the excess pore water will be dissipated during that 2 years. Okay. So again, this is just like kind of engineering judgment. So this one is usually done for saturated high plasticity clay soil that have very low hydraulic conductivity. And most of the time it's below the water table. Okay. So most of the time this one will be saturated. Now, if you see the state of stress of that two different situations, both cases, this one, the pore water pressure is not 0. So this one is the change in pore water pressure because of the confining stress. And this is the change of pore water pressure due to confining stress as well as the deviator stress. So both of them is actually creating pore water pressure inside the specimen. Now, how do we do the UU test? So first, make sure that the soil specimen is saturated by checking the B value. Okay, we can just use the back pressure here and measure the pore water pressure during the back pressure and try to make sure your change in pore water pressure with the change of your confining pressure is very similar to 1. Once the saturation is done, then you close the drainage valve and then apply required cell pressure. When you apply the required cell pressure, then basically the drainage is closed, so no consolidation will occur. So you don't need to wait for that to be consolidated. So you can just start applying shear by applying the deviator stress and increase until the specimen fails. The pore water pressure will increase during the applying cell pressure as well as during shearing. And record the deviator stress at failure. Okay. The added axial stress or deviator stress is essentially same regardless of the confining stress, because even though you are applying confining stress, all the stress will be taken by water. So basically your effective stress is not changing. If the effective stress doesn't change, then basically your deviator stress is not changing. Okay, that's basically the idea, that you are applying confining stress there, but since the soil is not allowed to drain or not allowed to consolidate, it means like all the pressure will be taken by water. So your pore water pressure is equal to your applied confining stress. So if you change that one, then your pore water pressure will increase at the same rate since your B value equal to 1. So basically, even though you are applying, like different confining stress, but since the drainage valve is 0 and it's not allowed to consolidate it, so basically your effective stress is not changing. If the effective stress means like the soil is effective stress on the soil is not changing, so the axial stress or deviated stress will be same for each of the cases, like when you change your confining stress. The failure in bluff for total stress, like Mohr circle become a horizontal line phi equal to 0. So you can see actually because of this one, like this one is not changing. So basically you will see like same, like size, your sigma 1 minus sigma 3 divided by 2, that's actually is the radius that remains same. Okay, but you are increasing your sigma 3, that's why your sigma 1 is increasing and this one is moving to the right. Now if you draw that horizontal line here, we call that one phi equal to 0. That's basically total stress scenario here, and you can see your strength is actually now horizontal. Okay, so what would be your CU? The shear strength of that soil, that would be from here to here, right? Now you can see here that your phi equal to 0, so your tau is equal to your C because phi is 0. So tan phi equal to 0. So sigma tan phi equal to 0. So your tau is equal to C. In that situation, basically your shear strength is a fixed number here. Okay, so only for saturated clay soil, your soil strength or undrained soil cases, your strength is basically a number. All other cases for CU and CD cases, that's basically your shear strength is basically a function. Why? Because your sigma is changing, your tau is changing. So your stress increased with confining stress. Here it doesn't matter. The confining stress doesn't matter. You know, it's like sigma 3 here, sigma 3 here. I'm just moving that sigma 3, but the size of the curve remain, size of this, you know, like um, Mohr circle is kind of same size. Okay, so try to remember that one. Your UU strength or undrained strength of saturated clay soil is a number. On the other hand, your CD shear strength from your CD test and CU test, that's basically a function of your sigma. Okay, and that changes with the confining stress. Here, the confining stress doesn't have any impact on the UU strength. Okay, so here is basically if you know the pore water pressure and you can just get that one off from there. So this is basically in terms of total stress, this one is basically your effective stress. So for both cases, you subtract the pore water pressure, actually you will just get for 4, 5, 6 different circles. If you test the pore water pressure out from there, then basically you will just get one curve like that. Okay, this is in terms of effective stress. You see, this is like bar. This is sigma 1 bar, sigma 1 or prime, sigma 3 prime. So this one is basically your phi prime, but usually we don't use that one. We just use the total stress Mohr circle at failure, phi equal to 0 situation. Okay. Now unconfined compression test. This is kind of a UU test that you don't allow the water to drain out during the consolidation and also during the shear application. But how do you do that? Actually, you run the test so fast on clay soil usually. You cannot run this test on sand because this is unconfined. Unconfined means like your sigma 3 equal to 0. So you cannot have any specimen, you know, like when your sigma 3 is basically 0 from the sand, right? You cannot make any specimen or cylinder from the dry sand, you know, like when you don't have any confining pressure. So this is applicable mostly for clay soil, and this is the load is applied rapid enough so that the excess pore water pressure cannot dissipate during the test. The UC test is done for clay soil as well as a rapid test. It takes very fast. The confining pressure sigma 3 is 0 for UC test. So you can see here that sigma 3 is always 0. Okay. And this is your failure stress. So you can see this is sigma 1 and sigma 1. Sigma 3 is 0. So for phi equal to 0 situation, you can see your CU or tau F is equal to sigma 1 by 2. So QU by 2, that's actually your tau F, which we call that one CU or unconfined, you know, like test, you know, like C value. Okay, that's what we are trying to show here. So you don't need any like triaxial sail, you know, like for this test. It's much faster, okay, because you don't have to wrap that one in the membrane, and you don't have to put that one in the sail, which takes long time. You can just cut it short, okay? So if you see this is the machine here, you can see you just make like the clay soil specimen. Um, Actually, we use like undisturbed soil sample from the field for clay and then basically cut that one like this. We cut that one in such a way that the height of this one has to be more than 2 times than the diameter. Then put that one here, and then you apply load from that top. Okay, also measure the strain here. Okay, so let's say the soil failed at sigma 1. So what's the shear strength of that soil? That would be sigma 1 divided by 2. What's the compressive strength? That's actually sigma 1. Okay, this one failed at a compressive force of sigma 1. But you can see the shear strength is actually half of that. So that's why soil fails in shear before reaching the, like the uh, failure due to compression. Okay, and you can see this is the line they are trying to show you, which is actually theta here, right? The angle is theta here. Okay, sometimes you don't see that failure like this. You can just see that the soil is soft enough that they are not breaking down, rather than they are just trying to compress and making bulge like this. In that situation, you just try to see like, hey, how much shear stress do you need to get, like 2% or 3%, like strain. That's basically your shear strength. Anyway, this is the unconfined compression strength of clay. We call that one QU. Okay, for unconfined compression strength, you can see that for very soft soil, this is 0 to 25 kPa. For soft soil, 25 to 50 kPa. Medium soil, 50 to 100. Stiff soil is 100 to 200. And very stiff is 400, 200 to 400. And hard soil greater than 400. Okay, kPa. And this one is like in other unit here. Okay, so that depends on like what kind of soil you are talking about. But anyway, in all the cases, they are completely saturated. Okay, very soft soil but saturated. Soft soil but saturated. Hard soil but saturated. Okay, because saturation has great impact on strength. So when we talk about strength, that basically it's always saturated. Okay. Now let's say example for UC test. This one is saying that undisturbed samples from a normally consolidated clay layer was collected during a field exploration program. Drain triaxial test showed that the effective friction angle phi prime is 25. Okay, the unconfined compression strength QU of a similar specimen was found to be 133 kilonewton per meter square. Determine the pore water pressure at failure for the unconfined compression test. We actually don't measure the, like pore water pressure, but we can just calculate that one from that equation here. That's what we are trying to show. So for confined compression test, your sigma 1 is given actually this one is written a little bit, this one has to be half of that, okay? A similar specimen, compressive strength, oh, that's actually not shear strength, it's compressive strength is 133. Shear strength is half of that, okay? So compressive strength is 133, your sigma 3 equal to 0. So in terms of effective stress, this one has to be sigma 1 minus pore water pressure at failure. So 133 minus excess pore water pressure at failure. And sigma 3 prime is sigma 3 minus excess pore water pressure at failure, which is 0 minus this. Now we know sigma 1 equal to sigma 3 times square 45 plus phi prime by 2. We already know the value of phi prime. And if we plug that value here, sigma 1 divided by sigma 3 is tan square 45 plus phi by 2. then basically we get this one is minus 90.85 kilonewton per meter square. Okay. Now you can follow the other equation, like your phi prime is equal to sigma 1 prime minus sigma 3 prime divided by sigma 1 prime plus sigma 3 prime, and you will get the same value here. Okay. Now, drained or undrained strength, that would be very, very important in your practical life. I'm sure that like when you go for any interview as a geotechnical engineer, they will also ask that question to you. So what is drain strength? So drain shear strength is used when the consolidation occurs before the construction of the infrastructure. All soils except saturated high plasticity clay. Soil usually drains faster, and drain shear strength can be used for design. Okay. So again, this is not about the soil only. It's also like how thick is that soil, the layer. Okay. So how much time does it require for 100% consolidation? And if you see your construction time is more than the time required for consolidation, then basically you can use drain shear strength. Because the drain shear strength is higher, most of the cases. Some cases it may not be higher, I'll talk about that in future. But most of the cases, your drain shear strength is higher, and you can use that one for design if you see that the soil will be consolidated before the construction. And then what is undrained shear strength? Undrained shear strength is used when the construction period is much shorter than the 100% consolidation time. So basically in nature, nothing is undrained situation. Everything will eventually drain. But how fast? That's the question, right? So again, that's not only for soil, also like the thickness of the soil layer and also like your construction time. So if you see that the soil layer, what you are designing for, will take significant time for 100% consolidation compared to the construction time, then basically you have to use the undrained, like shear strength from the UU test or unconfined compression test, which is basically as I said earlier, that very common for saturated high plasticity clay. Okay. Although the undrained situation is uncommon in nature, but saturated high plasticity clay soil takes significantly more time to consolidate it. So if you see like only 5 to 10% or 20% of consolidation will occur during the construction period, then it's always advisable to use the undrained shear strength, even though this is much lower than your drain, like shear strength. Now, comparison of UC test, unconfined compression test with the other UU test. So we usually expect that they will provide the same result, because UC test is nothing different than UU test. Only difference is like the sigma 3 is a little bit, sigma 3 is 0. But there is another difference is there, that in UU test we use like a membrane and the valve is closed, so basically there is nothing draining from there. For UC test, you cannot make sure that nothing is draining there. So sometimes we see that UC test results or unconfined compression test results could be a little bit different. So usually if you see here, this is your UU test and this is your UC test. This is triaxial undrained, unconfined undrained test, and this is unconfined unconfined compression test here. So this value is usually a little bit same, not like that small, but very close to your UU test, but you can see this is the vein test, which is done at the field. So most of the time your UC test is basically much lower than the field test, which is the vein shear test. Okay. Now shear strength of unsaturated clay. We are talking that every time if you talking about the shear strength, that's basically saturated shear strength, saturated condition. But what happens like if the soil is not saturated? You think about mud, which is very mushy and like uh, soft when it's like saturated. Just think about when this one doesn't have any water in it, like in it. So this one becomes like a rock. Okay, so it increase the shear strength significantly when the water is not there, or which is when this is not completely saturated. Okay, so that the shear strength of unsaturated clay can be written as tau F equal to C prime. And this is your sigma, but you can see this one is a sigma minus UA plus this function here into UA minus UW. UA is basically pore water pressure, pore water, not pore air pressure, and this is pore water pressure. Okay, and this one is a function that depends on the degree of saturation. Okay, so for practical purpose, where the cohesive soil may become saturated, the strength of partially saturated soil shouldn't be used. Okay, because eventually the soil will be saturated, and you don't want that your structure will fail because of the flooding or rain, right? So never use partially saturated soil strength for your calculation. Here is the picture you can see from your shear stress and normal stress, and this is like basically your degree of saturation. Okay, you can see your degree of saturation when close to 100%, actually your strength is not that high. Okay, on the other hand, if you see like only 61% degree of saturation, then your strength is here. Now, let's say for a very dry area, you just designed something using that, let's say your shear stress is like 600 kPa. You design something with that because you know, like it doesn't rain that much, let's say in El Paso, okay? But in 1 year, somehow it rained a lot down there and your degree of saturation moved from here to here. So you can see the actual strength is now 250, but you designed that one with 600 kPa. So what will happen? This one will definitely fail. So we don't want to take that chance. Okay, we just always assume that the soil is completely saturated. So that's about it. If you have any question, please let me know. You can always contact me by email and also come to the Zoom session during the office hours. Thank you for watching.